My first observation is Linux has an awful lot of file systems. If you look at the kernel sources and you look at all the subdirectories in the FS directory, you'll find 70 as of the 3.8 kernel. And with one or two exceptions, every single directory is its own file system. And so, the first question is, gee, why the heck do we have so many file systems in Linux? And there are a couple of different reasons. Let's break them down. First, we have the local disk file systems. So we have what most of us generally think of as file systems like ext3, ext4, Btrfs, XFS. And I'm going to call those the general purpose file systems. These are the file systems that are trying to be a good all-around default for most users. Then we have those file systems that are for legacy or backwards compatibility. So this might be HFS if you want to be able to plug in a hard drive that was originally formatted on Mac OS, or NTFS, ISO 9660 for those of us who still use CDs, so on and so forth. Very often the legacy file systems actually aren't as robust because they're generally intended for reading and maybe light purpose writing. But there's a lot of stress testing that generally doesn't necessarily happen with the compatibility file systems. So if you tried to use, for example, the BSD UFS file system as your root device and you stressed it a lot, I wouldn't be at all surprised if you found bugs because it wasn't really intended for use as a system file system, and so it hasn't gone through that level of testing and bug fixing. Then, of course, we have the remote file systems, both the network file systems such as NFS, CIFS, or SMB for those people who need to talk to Windows file servers. And then we also have cluster file systems that live in the kernel. Now, as we'll talk about later on, there are actually lots of other cluster file systems that are actually user space file systems. But things like GFS and OCFS2 are examples of in-kernel cluster file systems. And then finally, we've got the pseudo file systems, procfs, sysfs, debugfs, devpts. And basically what this shows is that Unix being designed around files. Files are kind of the core abstraction of Unix, and Linux has that Unix legacy in it. And so there are an awful lot of things that even though technically they're not storing data, using the file abstraction is just really, really handy. And so a lot of system interfaces you basically splice into them using the file system. So that's just sort of legacy of Unix. So the next thing I want to observe is that file systems are hard, right? Now, why is that true? Well, let's take a step backwards and say, what makes software hard, right? What are examples of software projects that if you were a programmer and you looked at that software project, you'd say, I'll bet you that's an accident waiting to happen. It's going to be really, really hard to make that file system be robust. And there are a couple of classic mistakes, or sometimes they're unavoidable characteristics of those programs. One is premature optimization. So the programmer is trying to make it go as fast as possible, and when you do that, you start adding all sorts of opportunities for race conditions and locking problems, so on and so forth. Also, if you have large amounts of internal state, that's a classic potential danger sign that your software may not be necessarily all that robust. And of course, if you use lots of threads and parallelism, again, lots of opportunities for problems. Okay, well, let's take a look at the characteristics of file systems. Well, first of all, people want file systems to go fast. And they want file systems to go fast for pretty much every single workload under the sun. And since you have one file system very often for all of the processes on your system, you've got lots and lots of parallelism, right? You can have potentially hundreds of processes or threads all trying to modify files in a single directory at one time. And we want that to be safe, and we want it to be fast. And that's actually really, really hard. And then the final characteristic, large amounts of internal state. Well, that's kind of built into the definition of a file system, right? A file system is trying to store data. And every single time you're storing lots and lots of data, there is an opportunity for that data, and in particular file system metadata, to become inconsistent. And so file systems are hard, which is kind of interesting given that we have so many of them in the kernel. So one of the things that I always like to tell people is that file systems are like fine wine. I don't know how many of you remember this particular advertising campaign. Dates back from the late 70s. From Paul Masson, "We will sell no wine before it's time." And you can imagine Orson Welles on a TV commercial. Later on, if I have time, I didn't have time to actually set up, but I actually had a YouTube clip of Orson Welles giving that 30-second sales pitch for wine. But it turns out it's actually true for file systems as well. So how long does it take to make an enterprise quality file system? Well, back in the fall of 2007, we had a workshop from people from Intel, IBM, there were people from Oracle there, Red Hat, SUSE, pretty much many of the large companies that were involved with the Linux community at the time. And we had a workshop called Next Generation File System. And the idea was that at the time, Sun was marketing ZFS very, very heavily. And the question was, okay, can we come up with a counter to that? Can we have something that has roughly the same feature set and target audience as ZFS? And so one of the things that I did preparing for this workshop was I did some research about, gee, how long does it actually take to make a brand new file system from scratch? And so I talked to a number of people who had actually made file systems previously, open source world, proprietary world, and you basically got answers that at the very, very low end was 50 person years of effort. In general, you got numbers that were more like 100 to 200 person years worth of effort. And that's everything from the original development to testing to performance tuning, documentation, all in 150 person years, give or take. And 5 to 7 years calendar time before it becomes enterprise ready. Now, every single time I tell people this, and there was no exception when I first told them this at the Next Generation File System Workshop, no one believes you, right? It's like, how could it possibly take that long? There aren't that many interfaces to file systems. How could it be hard? And the answer is, well, if you actually want it to be robust and performant, it really does take that long. So I want you to meet the ZFS team. This is a picture of some of the folks at ZFS celebrating when they had finally launched ZFS and made it public. Here's another picture of the ZFS team. They spent 7 years working on it. All right, and the number of people working on ZFS during the 7 years before they even announced it to the outside world ranged from, I believe, 5 to 7 in the very early years to around 20 right before they launched, right? 7 years. And then after they launched, right, after they publicized it, 6 months later, it showed up in Open Solaris and then Solaris 10. It was probably another 2 or 3 years after that before any system administrators were actually willing to risk mission-critical, production-critical data on ZFS, right? That's 10 years. It takes a long time to make a file system be fully robust. And it's one of these things that is always underestimated. So let me do a quick, brief history of local disk file systems. And we'll start by going all the way back to 1991 with the Minix file system. As the name might suggest, it's compatible with Minix. Linus used the Minix file system to bootstrap the operating system, and so obviously it made sense for it to be compatible with Minix. But it had amazing limitations. 14-character file names. You could recompile it so that directory entries were 32 bytes. in which case you had 30-character files, 30-character file names. And oh, by the way, notice that I said 32-byte directory entries. That meant you could only have 65,000 files in this file system, which was all right because you could only support 64 megabytes of data per file system. Of course, back in 1991, 64 megabytes was a lot of data, right? I mean, these were back in the days of 5, 10, 20 megabyte file systems, right? Disks, right? So, it was okay, but it became really obvious fairly quickly that that was not going to be enough. And so, barely a year later, we had the extended file system. And so we finally had variable length file names up to 255, 2 gigabyte file system sizes. Had a couple of problems. One was that it used the linked list for free blocks and free inodes, which meant that it was very, very vulnerable to fragmentation. Because what would happen is the first block that you would actually reuse when you wanted to allocate was the last one that you had deleted. And that didn't necessarily mean that the space was contiguous and files got fragmented very, very quickly. There was also only one timestamp, right? So traditional Unix, you have the last access time, the last modified time, inode change time. Well, both the Minix file system and the extended file system, one timestamp, right? This is starting to beginning to sound like, in my day, we walked uphill in the snow barefoot to school. But, that's really the way it was. So a year later, we had the extended 2 file system. And this file system tried to basically take all the best lessons that had been learned from the BSD fast file system. Because it was very, very clear at that point that there were a lot of things that we needed to do to actually get it right. And I think previous to that, the Minix file system and the extended file system weren't necessarily designed by people who were file system specialists. And so with ext2, that represented the first time that we actually started consciously trying to get the best that we could from the outside world. And then in '95 is when we actually rewrote the ext2 utilities from scratch. That's actually when I got involved with ext3, or ext2 rather, was I got tired of waiting forever for FSCK time, so I rewrote FSCK from scratch. And so one of the other attributes of ext2 was by now we had actually had 2 incompatible file system changes to work around limitations. And so we'd figured out that we'd better make the file system easy to extend. So the ext2 file system was the first file system that very consciously had backwards and forwards compatibility features designed in from the scratch. And so in some sense, ext2, ext3, ext4, you can think of them almost as one file system. It's just there are 3 implementations with differing levels of capability. But they're all fully backwards compatible. And in fact, ext4 can actually mount ext2 file systems. Now, let me take a quick sort of road not taken, because there were other file systems that kind of made appearances along sort of this main evolutionary trunk. One of them was ZiaFS, which was designed by Frank Zia. It had long file name support and A time, M time, C time support. It was introduced at roughly the same time as ext2. It had a limitation of files being no bigger than 64 megabytes. And you might think that was the reason why it didn't actually win adherence, although actually that wasn't the reason why. The reason why it didn't go very far was that Frank tried to rename ZiaFS to LinuxFS. He wanted people to say, well, this is going to be the default file system, and the way I'm going to do it is via marketing. I'm just going to change the name to ZiaFS. And people kind of laughed him out of court, basically. That was actually the true reason why ZiaFS didn't go anywhere. At the time, there were some people who were actually arguing that ZiaFS was actually more stable than ext2. And that was because ext2 was printing scary error messages every once in a while. Turns out both ZiaFS and ext2 had the same bug. ext2 just had safety checks that noticed there was a problem. And that actually allowed us to fix the problem much more quickly. And that's actually one of the other things with file systems is we actually try very, very hard to notice that there's a problem and fail early as opposed to letting data get lost. Then we step forward 7 years to ext3. ext3 is where we actually added journaling. And we added journaling in a way where it was fully backwards and forwards compatible with ext2. So you could take an ext2 file system, add a journal, and then you didn't have to back up restore your file system. You could mount it as ext3. You could take an ext3 file system, and as long as the journal had been replayed, you could mount it back on ext2 with no ill effects. And that made it really, really easy for people to actually experiment. Now, as it turns out, in 2001, there were actually 2 other journaling file systems that were competing with ext3. And that was because the reason why 2001 was the year where journaling suddenly became a real requirement for Linux was this was when there was suddenly this huge interest for Linux for use in enterprise computing. So shortly after 2001, late in 2001, early 2002, IBM announces they're going to invest $1 billion in Linux. Right? And so one of the things that you actually need if you're going to be doing enterprise computing is fast reboots after a crash. And journaling is basically one of the things that you actually need to make that happen. So there were actually 2 other candidates which appeared almost simultaneously with the ext3. One is RiserFS. RiserFS actually got merged into mainline 6 months earlier than ext3. And so some people will say RiserFS was the first journaling file system. And in terms of when it actually got merged into ext3, that's actually merged into the mainline, that's actually true. In fact of the matter, RiserFS and ext3 became stable at roughly the same time. So there's the question of when does a file system enter the mainline kernel, and when is it actually safe to use? And those 2 dates aren't necessarily the same. Hans aggressively merged early. Stephen Tweedy, who was the main guy who was adding the journaling feature, wanted to wait until it was actually pretty stable before he merged. The other one that actually showed up at about the same time was JFS. And JFS was an IBM submission. And in many ways, JFS was actually better than ext3. It was more scalable. In some ways, it was a more advanced file system. But the main problem with JFS was that the only people who understood how JFS worked at IBM. It had a development community that I won't say was closed. It was just that all the people who worked on it were at IBM. And that actually made it really, really hard for distributions to support. And that was actually why JFS turned into an evolutionary dead end. Then 5 years later, we had ext4, which was sort of a development fork of ext3. It was actually originally intended to be a short-term patch to fix sort of the hugest limitations in terms of 32-bit block numbers meant that we were actually limited and limited to 16 terabytes, and 16 terabytes really wasn't enough. People who wanted really, really large RAID arrays. The fact that we were using indirect blocks for really large files became a performance impediment. And so ext4 originally was going to address those. And then the plan was ButterFS was going to be the grand new file system that would actually take over the world. As we'll talk about in a little bit, ButterFS took a little bit longer to mature. And at this point, ext4 has kind of branched out, and it's found a lot of niche places where I think it's actually uniquely suited. So let's talk about ButterFS. ButterFS actually started in the fall of 2007, shortly before we had the next generation file system workshop. And you'll recall that at that time, I basically presented my research, which was everybody else says it's going to take 5 to 7 years. And everyone said, no, you can't say that. If you say that, the managers will never fund the project. So the official party line was, it's open source, so it'll be different. And that, in 3 years, we'll have it shipping in community distros. Well, that was 2007. It's now 2013, and 2013 is when we're actually first starting to see OpenSUSE ship ButterFS. So let's see, that's 6 years. Okay, about 5 to 7, right? So it actually took a bit longer than everyone thinks it would take, and that's just, sort of the way it was. Btrfs is designed to be very competitive with ZFS, so it has file system level RAID, file system level snapshots, data file checksumming, and if you need these features, it's the best file system for that. Now, one of the things about these features is, funny thing, they actually cost something. And so one of the things I want to talk a little bit about is the fact that if you don't need the features, you really shouldn't pay for them. But before we do that, I want to talk a little bit about the general purpose file system myth. I don't know how many of you remember Highlander, right? There can only be one, right? And for a long time, everyone kind of assumed that there should only be one file system that would be the best, and then everything else would be the rest, right? And there were a couple of reasons for that. One was it was considered too hard for users to choose, so let's just simply pick a default, and that default file system should be good for everyone for all possible uses. Another reason for that is way back when, if you think about the way things were 5, 7 years ago, there were many more time-sharing systems, or a server that would actually be serving multiple services at one time. And so therefore, the file system really needed to be good at servicing databases and web servers and who knows what else, because they were in fact all running on one disk at the same time on one CPU, right? These days, we actually tend to do scale-out computing and have specialized servers for specialized tasks. And so this idea that you need to have one file system that's good for everything at the same time is less important. And the big reason for that is workloads are really, really different. And file system design is all about trade-offs, right? Something that's actually good for one workload, say a mail server workload, where you have lots of small files that you're adding and deleting all the time, might not necessarily be all that great for a database workload, where you have large files that you don't really you don't actually allocate and deallocate blocks. You're just simply overwriting blocks of that in that large file. In particular, copy-on-write file systems tend not to deal well with databases, right? Unless you actually disable the copy-on-write features, at which point you've lost the whole point of the copy-on-write file system in the first place, right? So how did this myth survive for so long? And the main answer is that the dirty little secret is that for most workloads, it actually didn't matter. And it didn't matter because most of the time, the file system was not the bottleneck. Right? You were generally bottlenecked on something else, CPU, memory. And it generally wasn't the case that the file system was really what was actually critical. So, people would have fun saying, I like RiserFS, I like ext3, I like XFS. But in reality, you could switch file systems and it might not make much of a difference. And part of that was file systems were simpler. We didn't have as many features that we were trying to cram into the file system level. And then the big one was that back then, servers tended to be much more inefficiently run, right? People had done surveys before they started doing workload consolidation, pointing out that the average server was, if you were lucky, it was being used 10% or 20% of its full capacity. That 80% of its capacities were basically left on the table unused, which means wasted electricity, wasted power. And these days, especially for those of you who are into cloud computing, we're trying to run computers at near 100%. And so that was also one of the things where if you're going to be running things close to the edge, now you actually really have to make sure that your file system works well in low memory configurations, for example, which is one of those things that most people just simply never actually design for. So only pay for features that you need. I'll give you 2 quick examples for that. One is ext4 no journal mode. That's actually what led me to Google. I was the ext4 file system maintainer. And I started seeing these patches come in from Google engineers that allowed you to run ext4 file systems with the journal disabled. And I said, I guess that means they're interested in ext4. And I talked to them, one thing led to another, and I ended up at Google. But why were they interested in doing that? Well, it turns out that they were using, we are using ext4 as the local disk file system as the back end to a user space cluster file system. So if you search on papers for the Google file system, GFS, GFS is an example of a user-level cluster file system. Hadoop FS is another example of a user-level cluster file system. And those file systems have to provide redundancy and recovery against our hardware failures at the cluster level. Because if you have hundreds or thousands or tens of thousands of servers in a cluster, the probability that you lose a power supply, or you lose a motherboard, or you lose the network router that means you lose contact to all 30 or 40 servers in a rack is actually really, really high. And so cluster file systems have mechanisms that generally involve storing the data replicated on multiple servers on different racks to provide against redundancy. And in that environment, you don't actually need a journal. Because if you lose a server and the server has to spend 45 minutes running FSCK, you've got two other servers who can serve the data. Right? Now, as it turns out, when we moved from ext2 to ext4, the FSCK time went from 45 minutes down to 4 or 5. So ext4 is actually much faster at FSCK. But it turns out that even 45 minutes downtime after a hard reboot was okay, because the cluster file system provided that redundancy. And if you actually benchmark how much overhead the journal adds, it's actually quite significant if you're doing lots of small writes. Right? Lots of small file system transactions. Whenever you actually have to do a journal commit or a transaction commit in a database, you have to do an operation that fundamentally you can only do about 30 to 50 of them per second. Right? It's just not possible to do a cache flush any faster than that. And so you turn off the journal, you don't have to do those cache flushes. Another example is ZFS, right? ZFS has all sorts of really, really great features, but it turns out it's actually kind of memory hungry, right? So this is actually a quote that I found from an Open Solaris mailing list from other Open Solaris users talking about ZFS and using it. And the quote was, well, you know, if you're using a laptop and you don't really care about reboots, well, 2 gigabytes of RAM is enough that you can actually kind of survive. But if you actually have a server that does stuff and you actually want it to be reliable, you need at least 4 gigs of memory, preferably 8 gigs, and then whatever the application needs on top of that. Now, if you think about how much memory costs in Amazon EC2, you'll actually find that server instances with a lot of memory is actually really, really expensive. And that's because if you're going to cram lots of VMs onto a single server, there are limited DIMM slots, right? And high density DIMMs are actually really expensive. So memory is actually not free. Now the funny thing is that most people who do file system benchmarks do the benchmarks with nothing else running on the machine and with lots and lots of memory. But if that's not your situation, then your results will probably differ from the benchmarks. So the bottom line is you really want to pick the right file system for the job, right? File system design, all about trade-offs. And you really, really, really don't want to trust file system benchmarks, right? Number one, your hardware is almost certainly not the same as the benchmarkers, and hardware makes a huge difference. Secondly, the workload that you might want to be running on it may not be an accurate reflection of the benchmark. So the best benchmark that you can use for a file system is your workload, right? So if you really, really want to test, you should take your workload, run it in a test environment, and use multiple file systems and see if it makes a difference. Because what might work well for one workload and one file system might be very, very different for another. So, a couple of last thoughts. File systems are not databases. Right? There are a few exceptions. RiserFS was actually one where there was one of those snide comments I would sometimes make, which is RiserFS is the perfect file system if what you want is a Windows registry, right? Because it was actually designed for small files being really, really fast. But in general, file systems are not optimized for small files. So if you have lots of small files and you want to add and delete them, use a real database, right? Use MySQL, use SQLite. they will probably do a better job than trying to use a file system and directories and small files as a database. Another thing, user space cluster file systems. If you need to serve up huge amounts of data and you're in a cluster environment, you really, really want to think about using things like Hadoop FS, which is the open source file system. One of the other things is keep in mind that the file system is only a small part of the overall storage stack, right? You've got the file system, you have applications above the file systems, which might include databases or other technologies. Below that, you might have an LVM, and you might have hardware RAID, storage attached network, SAN devices, and there are plenty of other places in the storage stack where you might actually try to solve a problem. So I'll give you an example. One of the technologies that will be coming up very, very soon is something called thin provision snapshots. And this is basically doing snapshots at the device mapper layer. And so what will happen is when you take a snapshot, as the file system actually tries to allocate new space, the thin provisioning layer will actually pull space from a spare pool of blocks and use that to maintain copies of the snapshot. And then when you delete a file, the file system will send a discard notification to the device mapper layer, and then the device mapper layer will release the blocks. This basically gives you a lot of the benefits of file system level snapshots, but allows the functionality to be separated and implemented in two different layers, which is actually kind of cool, because now you can actually say, all right, I need file system level snapshots, but I might not need them all the time. And my performance characteristics might be such that I really need some other file system, either XFS or ext4 instead of Btrfs. Well, with thin provision snapshots, you now have a choice, right? And so that's an example of, even if you need to take lots of snapshots, sometimes the answer is it doesn't have to be solved at the file system. Another example is something called F2FS, which is the flash-friendly file system. Some of you may have heard about that. The Samsung hardware engineers in the flash division actually implemented that. And they implemented it because they were actually trying to improve performance on Android devices. Now, one of the things that they actually did in their design, which I think was a mistake, was that they assumed that SQLite was a fixed point, that you couldn't actually swap out the user space database. And that was because they were hardware engineers, right? The fact that they were thinking about doing something in the kernel was thinking out of the box for them. But it turns out that SQLite is actually amazingly inefficient. And there is something called the Lightning Memory Map Database, which is actually part of OpenLDAP, which has a drop-in replacement for SQLite that has been benchmarked as being 10 times faster than SQLite, right? Now, there are some good things in Flash2FS, mainly knowledge of erase blocks, and I'm not saying that Flash2FS is a bad file system, and I'm glad that they did it because it's now introducing new ideas that we can now all look at. But the fact of the matter is it's going to take 5 to 7 years before Flash2FS is actually ready for prime time. And by then, SQLite will probably have released another major version. So designing a file system to target a specific user space application can be a little bit dangerous. Not sure it's actually that smart an idea. So some future file system challenges. What do I think we might be doing in the future? And it's all going to be about accommodating different types of storage media. So we have accommodating fast media, PCIe attached flash. That should be flash, not file system. So Fusion IO cards, these are cards that are going to be really, really expensive, but will allow you to have thousands, possibly hundreds of thousands of transactions per second by using lots of flash channels in parallel. And file systems have been traditionally architected for hard drives that were orders of magnitude slower. And so there will be changes we will need to make in the file system and in the storage levels to actually deal with that really, really fast media. Another challenge, the exact opposite end of the scale, accommodating cheap media. ext4 is being used in mobile handsets. One of the things about mobile handsets is the cost of the bill of materials is critically important. And so eMMC flash, or what you might find on an SD card, is super, super cheap, which means it has a lot of limitations. And so designing a file system around that is going to require some challenges and some changes. Flash2FS is an example of a file system that's working in that space. Finally, we have accommodating slow media, shingled drives. Shingled drives are drives which are sort of like flash, but using hard drive technology. So reads are fast with shingled drives, but if you want to modify a block, you generally have to rewrite something like 32 to 128 megabytes of data, and it's at hard drive speeds, because you actually have to write an entire zone. Shingled drives, I think the jury is still out about how important shingled drives will be in the future. And the main reason for that is that these days, generally the problem with most workloads is that we actually can't get to the data fast enough. It's not that we need more space, right? So, I've got half a terabyte on my laptop. I don't use it all. It's not clear to me that I need 10 terabytes of space on my laptop, especially if access to it is really, really slow, right? So shingled drives may actually turn out to be the next generation tape drive, as opposed to the next generation disk. But there is research work about how would you actually make a file system that can actually accommodate these restrictions for shingled magnetic media. And then finally, we have accommodating fantasy media. And by that, I'm talking about resistive memory technologies, which has been 2 years out for the last decade, right? So, every year they say 18 months from now, we will be shipping product. And resistive technologies are supposed to be like flash storage, except it's as fast for reads and writes as memory, as cheap as hard drives with no write cycle limitations, which sounds like the Platonic ideal. And if it exists, then file systems will actually change by a lot, because you might actually start executing off of this resistive memory technology, right? So it would be almost like DRAM, except it's hard, you might have several gigabytes of it, and it doesn't go away when you turn off the power. If we have that, we'll probably be re-engineering the operating system to take advantage of that. On the other hand, it's been 2 years out for the last decade, so I'm not holding my breath for when it shows up, because I suspect when it first shows up, it's going to look a lot like Flash, right? And so we'll see where it goes from there. So, in conclusion, file systems are important, right? And they're important because Unix is designed around files, so it's one of the core abstractions in the operating systems that we all know and love. But at the same time, file systems in some ways are kind of overrated because they're only one part of the storage stack. And these days, a lot of the really, really interesting work is actually above the level of the file system, or at least the local disk file system, right? So there's a lot of really cool stuff happening in the database land in terms of user space cluster file systems, and that's good, right? I mean, we have a lot of file systems already. I'm not sure, having had 70 file systems in the Linux kernel, that we need another 50 file systems. But using file systems is actually what's really cool, not creating file systems, as much as I actually like doing that. And so the reason why I keep doing it is because I actually find file systems to be really interesting. Hopefully you've gotten a glimpse as to why I think they're really interesting, and you may find them, hopefully I hope you find them interesting too. But we'll see where things go. I think file systems are really cool technology. We'll probably still see some development on them. But please don't forget that file systems are only one tiny bit of a much, much larger story. So thank you very much.